there is a certain limitation that free energy possesses. So one
so one word for session is to get some sort of
right. Come on.
Right, so one word for session is to get some hands-on some sort of idea about what the free energy is. Along with that, I also want to cover some important thermal concepts which are not taught in school, right? And they not everyone can really just those who are in concept line, because I believe there will be some music also. Including some practical stuff. So we'll cover this stirring engine and internal combustion engine. Right? Our engines, as we know, are one of the first inventions that humans made based on their knowledge of science. I mean, the knowledge and all were based on just geometry. Right? This is one of the proper first applications of our scientific knowledge. So I believe that engines are very important. They will remain important even in the future. As we move to, let's say, fusion power, right? Even then, when you create energy, through what mechanism are you going to extract these fast moving neutrons and then convert that to electricity to our homes? These are engines. Right? So, engines and the study of thermodynamics is very important, as you can see. Okay, so I'll quickly tell you the principles necessary. Let's say thermodynamics. Familiarity with PV diagrams. I'll give you a small example over here. So, if you guys are able to understand what's happening here, you should be able to follow the rest of the lecture. Okay. What is this over here?
Carnot angle.
Right, Carnot cycle. It is the Carnot cycle is an example of what is known as a reversible cycle, a reversible process. You would have seen many definitions of reversible, so let's say I won't go into what that means. But one of the conditions for really being very efficient is that our process must be reversible. I mean, I won't really define it properly because most of you already know it. But the intuition behind the reversible process is that you have to kind of handle the system with care. Okay, we'll see what this means for like. We'll see what it means. The third requirement is for imagination. Right? Okay, then since many of you guys already know the Carnot cycle, I will start with a slightly different engine. This engine was the Stirling engine. It was invented in 1816 by Stirling. It was not one of the first engines around. When you look at the history of engines, it began with steam engines. Steam engines were invented around the very end of the 15th century, 1688 or so. But the real popularity of steam engines started at 1712. Right? I think something in New Home. This steam engine was used to draw water from coal pumps. Pump water from coal mines. That was the first practical application of steam engines. Even if you also that we use in Britain. Now the question, so let's just look at the Stirling engine for a while. And what we'll try to do is improve its efficiency, see how we follow Stirling's areas. So, the steam engine uses a certain working fluid. The working fluid is not gas present inside a certain enclosed container. That's the enclosed container, and there is a certain gas present inside. This is in contrast to the steam engine. Steam engine is very rudimentary. The way steam engine works is to boil steam, maybe we should draw it. There will be a certain boiler here. And you kind of give a lot of heat through coal. So this here would be a high pressure boiler. In fact, the original steam engines were actually worked with very low pressures because the metallurgical technique necessary to make thick boilers was not available that day. So they were very efficient to begin with. And from these boilers, the steam would enter. Well, there are many versions of steam engine. I would probably take this one. Right? So the steam would enter one of, let's say, one of two areas. And here the link is in color.
those will be two, let's say, valves per hour. So what will happen to the steam engine is there will be a certain regulator over here. So what will happen to the steam engine is that this boiler will create high pressure steam. This steam is going to flow into this chamber and it will push this, I don't know what to call this, maybe call the piston. It will push this, let's say, complete separation. It will push this to the right till finally the plate reaches over here. While it pushes to the right, whatever air over here gets just pushed out. Right? There is a high pressure steam being pushed out. Now after it comes here, not exactly there, more like over here. Now after it comes here, this regulator will switch off the flow to this one and it will open the flow to this one. At the same time, this wall over here is going to open, while this wall is going to shut tight. And now you have the same thing happening in the other direction. So the steam is going to push this plate to the left till it reaches here, and then the cycle repeats. This one wall, the gas is left this wall. This will shut tight. This will be open. Steam will enter here. The displacer will move to the right hand side. And this reciprocating motion is how the steam engine, the consider steam engine used to work. I guess in many variants of this. But now Stirling's idea was Stirling's idea. It was one more design here. The design is rather than having keep on emitting steam like this, you would try to create an engine using a single working fluid. In this case, it's hot gas. So let's see how this works. The steam engine, the Stirling engine cycle, so it begins with a temperature source. This one could be from coal, from gas, so on, and another cold temperature, sink. This cold temperature is normally the icy weather in England. So as this hot gas on this end gets heated, the first step is it will expand to the right and push. Okay, so I should specify that there are two things here, right? So the construction of this involves this sort of this chamber. Inside there are two pistons. This one here is known as a displacer piston, right? Displacer piston, and the other piston here is the one which actually does the work. So in the first step of the Stirling engine cycle, the gas on the left expands and pushes this to the right till the gas is reached, till the piston is expanded to as much as it can. In the second step, this hot gas over here, which has been absorbing heat and expanding, it moves through the sides of the displacer piston. And again, different designs use different techniques. In some of the techniques, rather than moving through the sides, it moves through perforations within the displacer piston. Or perhaps, well, there are various techniques. So it moves here to the cold side. After reaching the cold side, it gives all its heat away to the cold side and reaches that state. And this, in the process of losing heat, the work piston does not move at all. The work piston remains like this. Okay.
So the steam piston doesn't move at all.
No. So when you expand the gas, both the displacer and the ring piston move together to the right. Okay. You may be wondering what the purpose of the displacer is. So it's just to be more around. So the first, both of them move to the right. Now the second one, only the displacer moves to the left. The work remains exactly where it is. So the purpose of the displacer, as the name suggests, is to displace the hot air and make it cold, and vice versa. Okay, so this thing comes back here. You could of course do this in, like I said, there are different ways to implement a single engine. This is just one of them. So in this particular implementation, the displacer is simply displacing hot and cold air. The total volume of gas remains the same while the displacer piston is moving. Where the gas is, that changes, but the volume of gas remains the same as the displacer piston moves.
do that here. Right. So in the first step, there is an expansion. If the volume increases, this step here, that corresponds to this one, the expansion of the gas. In the second step, so it's not getting confused. P here refers to how much load is acting on the piston. It's not an active separator or something, it's how much load is acting on the piston. While V is the total volume of gas. Expansion. Now over here, keeping the volume same, there is a loss in energy. That refers to the cooling of the gas as it reaches the cold state.
Wait, so like, is the green piston and the blue piston like attached to each other, or is it?
Okay, so they are not attached. They move independently. How they move is another question, we will look at that. But they are made to move independently.
Oh.
Two independent pistons, they look attached here, but the fluid is not drawn the mechanism by which they are controlled.
Oh, okay. So they are moving independently of each other.
Yes. Is there anyone else who has similar place?
What is the shaft? What is the role of the shaft?
Role of the shaft. Okay, a shaft would be the wrong way to put it. This is technically something that controls this piston. You will see, I will show you. This is the shaft. This is how the control of the piston is.
Wait, since the gases on both sides of the blue piston are mixed anyways, then what's the purpose of the blue piston?
Okay, they are not mixed. They are. That's a point. We are assuming that the thing is moving fast enough, and the gas is flowing through these slow enough that there is no mixing. Okay. Again, you can do this in different techniques. If you really want to make it separate, you can have two different systems. That's another arrangement. This is not another. We are assuming the gas flows very slowly.
Okay.
Because there is a very thin space, very thin gap. Okay. Right. So the second step, the cold gas, gas is cooled down, moves back to the hot side, aided by the displacer which pushes it to the hot side. So now all we have is a lot of hot gas over here. Okay. The gas moves cool side, now this comes back and comes to the hot side. Sorry, 1, 2, 3, 4. 1, 2, gas moves cool side. That is this one. Now there is one more compression step. So all this cold gas is now compressed. The displacer remaining where it is, so the hot side has no gas. But the cold gas is being compressed by the piston. Of course, any heat generated during compression is taken out. That's
Could you explain the stages, but also explain how the pistons are moving?
okay.
Yeah, how the displacer is moving.
So it is best to show an animation against to how it moves. It moves based on this particular mechanism. Again, the animation will make it as clear as possible.
But I want to understand, like in each, like in the previous slides, like how is, I don't know, like how they are moving. Like we'll just explain, like okay, this is moving close to this.
Okay.
And how does that green piston come back?
Okay.
After 4 steps, the green one went forward and never came back.
No, we are in the third step. So the third step, the green piston remaining where it is compressed. Now in the fourth step, this compression is such that it can compress back to the same volume. In the fourth step, this piston moves backwards. So yeah, this compression is where the green piston moves back. Then the fourth step, the displacer piston moves back here, and displaces all the cold air back to the hot side and again back to the
So
starting
is
stage.
it like in each step, like one piston remains fixed, the other one is moving, and then in the next step, one piston remains fixed, the other one is moving. Is it like that?
Yes.
Oh,
So, if you look at this diagram, you can think that the isothermal curves are taken care of by the work piston, the green piston, while the constant volume steps are taken care of by the other piston.
so this TE diagram is for what part of the gas? Because see, now I have two gases. Like, so we
So it is the entire thing. There are not two gases, only one gas.
no, but then like those two gases have different states, right? So like which one are we taking here? Because they will have different pressures, different volumes.
Okay, so I should mention the assumption more clearly. These gases, we will not consider them as two separate stages. I am simply showing this in the process of motion. Actually, the main steps happen while the gas either are here or here. So this step here, all the gas on the hot side is expanding.
Yeah.
In this step here, after the gas moves, has finished moving to the cold side, we assume that the motion is, let's say, doesn't take so much time. As the displacement moves to the left, the gas automatically moves to the right. Now, once it reaches here, then it cools down. So once the piston reaches here, once the displacer moves, right, only then the gas cools down. So the way to think of it is that the gap is very tiny, so there is little interaction. What really forces the gas to move is the displacer moving to the left and right.
Okay.
Once the displacer displaces the gases, then the gas cools down. So there is no step on the cycle in which we are not considering this the dynamics of this. Right? Why again for a proper for actually engineering this you will definitely have to consider dynamics. Right? But we are simply trying to get a theoretical model of this. We will see because of the practical concepts right. Right. So 1, 2, 3, 4. 1, 2, 3, 4.
Second step, the displacement is moving towards the left.
Second step, yes.
And gas is moving towards the right.
Yes, so you can see the direction of the arrows. Then move on the direction. What is the first step? Third step, then compression of the cool gas. So this is step 3. The cool gas compresses. Yes, work is true. And then it's basically limits. Okay.
Can you move to the previous slide?
Yes.
Yeah, so do you consider the left part as the cool gas compared to the right part?
So, the left from your perspective is hot gas and the right is the cool gas.
The third picture.
Third picture. Okay, it is not very accurate. It is separate.
No, how? But how?
Oh no, okay, the picture is not drawn properly. You should imagine that the displacer move completely to the left. It's like this, displacer is fully right.
No, that's the fourth step, right? But during that process,
Yes.
there will be gas there, right?
That's the point. The displacer move completely to the left. So there's no space for gas to be there. All the gas come here.
No, what makes it to move?
This when this one moves, the gas is forced out of here and over there.
Yeah, okay, but it's still there's gas heating on the left-hand part, right? So, like, how will it, like, if the pressure on the right-hand side is greater than that on the left-hand side, then the displacer will move.
In over here.
Yeah, on the second picture. If the pressure on the right-hand side part is greater than that on the left-hand side, then the displacer will move towards the left-hand side, right?
No, the displacer is controlled. So both the displacer and the work piston are controlled from outside.
Control.
Yeah, that's so control is that you will see the mechanism, but it's you are making them move in a particular manner.
So it's someone that's controlling.
It's not someone else, it is a mechanism. It's like if you roll a ball down ball, it can only move in certain way, no other way. Similarly, the mechanism is such that the big piston can only move in one way, the other one can only move in one way.
I think there's like a wheel and then there's a crank and the pistons attached to it.
So the relative displacement between two pistons is always going to be same. The fixed motion. How fast it moves all that depends, but it's a fixed motion. And there's not a conflict between dynamics and statics. Okay. So many of you guys are having this talk about how fast is the gas moving, or for instance, this tiny space, how does the gas move, pressure differences and all that. Then let's treat it as a one single system. There's one pressure, one volume inside. Okay. Dynamics we will let's say as an approximation, let us think that for now. If you want to design it, make an actual machine, you will have to learn from that. It's important to understand this cycle properly. It's a very ingenious engine. Does anyone else have any similar confusion about this? We'll be using this engine a little more. So, is there some? Yes. So there's a good website. You see the image there. Actually, this website has multiple types of engines. So it's an engine exploring more different types of engines. Right from motors to the water grounded. So now you can see the full motion in action. Compression of the board. We will slow it down looking forward. So compression of the cold gas, the expansion of the hot gas. You can see also that this is not an exact cycle like I drew. Because of the limitation of the mechanism, we will not get the exact degree relation that we were looking for. But if you have to try to understand this engine from a particular analyzing engine.
Bottom right. Bottom right.
Okay, so we consider the efficiency of this engine. I've color coded what is happening. You can see the arrows. So here there is heat engine, which stage of the cycle is this? Just to okay, which stage is this? Pressure is increasing at constant volume. Expansion of constant volume and pressure is increasing at constant volume.
No, it's like the fourth step to the first step, the transition part.
Right. So gas moves to hot side and then heat up.
The fourth step to the first step. Like it's going to start the first step. It's about to start, but before that. Wait.
Okay.
I wish I had chocolate in my son. Okay, next one. Now we have an isothermal step. This is an expansion. First step, yes, correct.
First step.
Next, cooling.
The second.
Second, yes. And finally, isothermal
The
compression.
third.
Okay. Quickly I'll do this. Not done this. Given various formulas there, I think you have to sometimes it works done by both of these stages. The heat input is on the one hand due to the heating, and then there is some heat input over here as the compression happens. Output heat is also here. The efficiency we define as the work divided by the input heat. And the formula comes out to be the temperature at the hot side of the engine minus the cold side by temperature at the hot side plus. Okay, now we have some factor over here. How can this particular factor be, how do we get the maximum efficiency here? So you can see it happens as the ratio of the volume goes to infinity. What is the ratio of volume going to infinity be practically? That is a physical thing.
Not an enclosed space.
Not an
Enclosed space.
Okay, yeah, it's not enclosed. How much work are you going to get out of this? Look at that for a second. The amount of work done is all inside. Now the ratio of volume goes to infinity. Work also goes up to infinity. And if we want infinite work, we need infinite heat also. So it's really not feasible at all to aim for such an engine. So this is one limitation of the Stirling engine, or more like this is not the actual Stirling engine. So what really makes Stirling engines quite famous is his solution to this issue. So think back for a second to the point where we talked about reversibility as being essential for efficiency. In which step are we using our efficiency?
Second to third and fourth.
One. Okay. You mean this step and this one, right?
Yeah.
Right. So what is the issue here? That we are transferring heat from a hot to cold one. The reverse process can happen. Right? Heat only goes from hot to cold. And there is a very much a finite temperature difference. So this is one of our problems. And Stirling had this was Stirling's main idea, and his what he wanted his patent from that. Clearly, the two steps where heat is absorbed and given out at constant volume hurts the efficiency. This invention was something known as a regenerator. What it does is it will absorb energy as the gas flows to the cold side. Right? The gas will give up its heat energy to this regenerator. And as the gas flows back to the hot side, it will heat it up using the previously absorbed heat. If you look at this, right, you can see that both of these expressions are the same. Both of these expressions are the same, which is obvious, right? They're heating from the cold temperature to a hot temperature or the other way. And Stirling's solution was to rather than let this heat come from the whatever is producing a hot temperature or simply heating out the surrounding, you just store the heat in one cycle and give it back in the next. Or one part of the cycle and give it back in the next part of the cycle. So what you are seeing over here, which I did not mention before, these are known as heat exchangers. So as the gas flows from here, the hot side to the cold side, right? And this heat exchanger, as you can imagine, will also have a similar temperature gradient. One side of the heat exchanger will be hot, the other side of these fins will be cold. And if these fins are somewhat large, we can say that these heat exchangers effectively work like a system of reservoirs of multiple temperatures. A system of reservoirs of multiple temperatures. And as the hot gas flows to the hot side to the cold side, it will one by one give up a small portion of the heat to each of those different temperatures, and in a reversible manner it will cool down to let's say the room temperature and the London temperature. And vice versa, so as it goes back to the cold side to the hot side, it will step by step gain the same heat in a reversible manner.
And how does it accomplish like how the reservoirs place?
How the reservoirs place? Okay, now you are asking the practical question. Good. Practical, right? Yeah, so I told you theoretically yes, what is reservoirs. Practically, there are multiple ways to do it depending upon the scale of your engine and so on. So one common technique used is to place what is known as wire houses. So you have multiple these nets for your wires, you roll them together, and a certain pipe through which the gas will flow, or you roll it around this system. Multiple techniques. Or maybe you just wrap the full engine here with a bunch of wires. That's one way. Have any of you guys seen the coffee stirring machine? The coffee cup machine. Right, so you know how the heat exchanger there works. So that one has I believe it has a styrofoam heat exchanger. So it's like the foam, there are many holes to it. So rather than the air passing through these gaps, the air passes through various holes within this displacement system, and as it passes, it exchanges heat going from this styrofoam. And that is one technique, is very small scale. So it depends a lot on the scale of the machine. The heat exchanger, that is the theory. Right? So some certification can be used in 2002 or 12. 2012, NASA tested a nuclear fusion reactor in outer space. That was also built on a Stirling machine. Then the construction was the same principles but very different things. There it was liquid sodium, and the heat source was uranium-238. Or I'm making an example.
238.
238.
238.
Okay. Fine. So that's the concept of heat exchanger. With the heat exchanger, we see that we will no longer have these terms because they will stay within the system, and the efficiency gets drops down to, because this term goes away, 1 minus the cold temperature divided by the hot temperature. And this, as you would have studied before, is nothing more than the Carnot efficiency formula for an ideal engine. There is the flow engine that we do better than this. It's a perfectly reversible engine. Okay. Very just one small thing. Again, supposing I were to do a small change here, right? Rather than putting heat here, supposing I keep the heat here and put the cold side over here. Right? What is that result? So rather than giving the heat on this end, right, and removing energy from here, suppose I keep the heat here and remove energy from here. I take a starting engine, but I put my candle on the cold end. Then what kind of machine does this become? Right? Refrigerator. Of course, at this point, rather than extract work, you have to clean work. This becomes an ideal refrigerator, also known as a heat pump, also known as indefinite. Okay. So the main issue with the heat engine is that this is limited by the temperature, and this temperature has to come out of a certain fuel. Right? And in order to find out how efficient this engine is, we need to think of it from the perspective of how much temperature is our fuel capable of producing. Okay. This is so the efficiency of such an engine is limited by how much temperature can the fuel pass. And before trying, so if we want to improve the efficiency of this engine, right? Again, you would have seen that, okay, Stirling engine is ideal efficient. Stirling engine is ideal for a heat engine. But our engines we are interested in are chemical engines. Right? Heat engines has its own interest, solar power and so on. But what we are interested in is extracting energy from a certain, for now, let's say a chemical substance. Right? So in order to understand how efficient can our engine be, we will have to understand how much temperature can this. I mean, we will have to see there are other ways, but we will have to understand how much temperature can be produced with a certain fuel. I'll take one example just to give some idea about this before we try to automate it. Stirling's original drawing is over here. Okay, that's the drawing of its original engine. We included this land. This engine, like I said, was used in coal mines. The fuel for the Stirling engine was something known as flue gas. So flue gas is a mixture of carbon monoxide and various other stuff. It is often found in coal mines, pretty dangerous. Byproduct of station and so on. So what we do is we consider a simple coal-powered Stirling engine and try to evaluate how efficient this can be. Okay, and then maybe improve on it later. So here is one such design. I can redraw it in my own way. This is a certain reaction chamber. Okay, it is a power plant chamber so on. Someone feeds coal into the bottom. At the same time, there is a fan which draws in the atmosphere. This atmosphere is a mixture of nitrogen and oxygen. If you want to separate the nitrogen and oxygen, you think that will give better efficiency, because nitrogen is a single thing. That process separation itself will take some of the energy, it's no use. So let's just take it as it is. Okay. So we're taking nitrogen and oxygen at room temperature, which I assume is around 300 Kelvin. I burn it over here. Okay. In the process of burning, can we quickly just keep track how does what happens where does heat flow? I mean, as entering at a low temperature, the chamber is very hot. So what is the first heat transfer which happens?
The chamber is the
So air heats up. Right, so certain amount of energy is given to that. Now after that, he has going to combust. So now release energy. Okay. Releases energy, and that energy is taken up in Stirling. So some of that energy is of course put back into the chamber. And what? You have to heat the air, right? You have to heat this air up. After it combusts, some part of that energy must make up for the energy required to heat the air. Whatever is left, can now be given to the Stirling engine and converted to work. Right. And of course, we must regularly remove the waste products. If you want to really optimize efficiency, we will have to put some kind of heat exchanger over there also, right? Power plants do that. So one heat exchanger goes there, and from the exhaust gas also 30 days of heat. So now as simplicity, legacy calculation, we will go there. Right. So let us before I get into this calculation, there is one more thing we have to keep in remember actually. What is JD? Have any of you guys studied about the Gibbs law of chemistry?
Yeah, like there was something that I think was that like whichever path you do a reaction to, the amount of energy you take is same.
So that is the first of the thermodynamics. Gibbs law is called a formula that comes out that way, right? It has to do with the enthalpy of the reaction. So as you heat the reactants, the enthalpy of the reaction tends to it changes. Okay, so at a new temperature, the new enthalpy will be delta H is original temperature minus the change in NCP. So I write this over here. Delta H as a function of temperature equal to delta H at some, let's say, 300 Kelvin minus delta of NCP. N refers to the number of both the reactants and products. Okay, delta here means as you go from the reactants to the products. Okay, so as you go from reactants to the products, the number of moles multiplied by the specific heat of that particular substance, which is like the specific heat of the total mixture. Okay, the change in the specific heat of the total mixture, and multiply that by the change in the temperature. And the change in the temperature is T minus 300. So this is the way to derive this is like by first law of thermodynamics. Briefly, you can.
What is that delta R to T and then what is that Cn?
Delta of NCB, right? CB is
NCP.
yes.
It's in bracket.
So you can
Okay, like that.
so this is the how much is the specific heat of the final products differs from the specific heat of the reactants. So why this matters is because as they heat the temperature, as heat the reactants, right? And they heat the you start with this much energy in the reactants. Once you heat it, the reactants energy goes up because of you're heating it. While when it comes to the products, right? You start the products. The product will be at a certain energy about this, right? But it could be that the amount of heat required to heat the products is much higher than that required to heat the reactants. So if these are different, you go up here, right? Then you react, and then you come out by to keep that balance of heat, you have to change the enthalpy also. Right? Anyway, that's how it's derived in school. I can give you one slightly more interesting intuition if you want, right? Or will you go ahead? So anyway, in this particular case of Boltzmann is not very important actually. The reason is because Bol plus O2 gives CO2, right? Number of moles of gases are the same, and the CP is totally similar. So it doesn't make a difference both the molecules. Okay, but this will be important for other reactions. And in general, we have to make very accurate calculations about the efficiency of a heat process. it is definitely very important to study the chemistry of or on the full properties of the reacting molecules. Right? And then the specific heat is quite deeply related, as again we will see in some time. Specific heat is very much deeply related to the molecular properties of the substances. Right? You may think ideal gas, everything is on F by 2 and 3 by 2, 5 by 2, but it's not just about real gases and ideal gases. There are more different especially at low temperatures. Okay, so there is a change in enthalpy of the reaction, which for this case we are not going to take into account. Let me quickly run through these calculations. So, 1 mole of the fuel absorbs this much, let's say, reaction at the constant pressure, and if you put a constant volume, that may be better than water. It's not very practical to constant volume in high temperature reactions. So, let's go to constant pressure. So, it absorbs this much energy, gives us a certain delta H, which is basically the same. The efficiency of the engine is, so that's the swelling efficiency, multiplied by, now there's one more factor, which is effectively take care of how much heat actually lost to the because it has been heated up. And I brought a graph of this.
I had saw the second term was like the other factor which is less.
This one.
Yeah.
Exactly. Delta. No, so out of the so the efficiency of this process I will define as again you can see now this may not be the best definition, but I will define it for now as the work extracted divided by the enthalpy of the reaction.
Enthalpy of the reaction.
At room temperature. You might be asking why at room temperature, is there any special about room temperature? Right? But okay, we will define it as the work extracted divided by the enthalpy of the reaction at room temperature. Now the work extracted is out of delta H, right? Only delta H minus Cp into T hot minus T room is left over. And some energy has to go into heating the product, right?
Heating the product or like
Heat the reactor. So as the atmosphere enters and the coal is put into the chamber, it has to be heated up. So out of the delta H, right, only delta H minus that energy which is heated up is left over for to be used.
so that second term accounts for the air getting heated up.
Yes.
So first term is efficiency of the slurry.
Yes.
And the second term is efficiency that is because of heating.
Correct. So one of them, as you increase the temperature, one of them becomes better, while the other one becomes worse. So there's a trade-off. You have to find what is the optimum temperature. If you go to a very low temperature, then the reaction, there's no wastage in heating of the reactants, but at the same time, the machine is not very efficient. If the temperature becomes too much, it may be so that you get overheat on. You have to heat up the reactants to such a high temperature that it's not able to clear it, it's not able to cover up. Okay, I put my specific values 300 Kelvin and the delta H of coal is 7000 kilocalorie per kg. The specific heat of coal is 0.50 kilocalorie per kg. If I include the heat going to heat of nitrogen oxygen, there is a 0.75 kilocalories per kg of coal specific heat. Okay. Again, these are approximate. You have to remember that this is also approximate one. That specific heat is not a constant temperature. For first order approximation, assume it's constant. And we can see that so 0.75 kilocalorie is required per kg of coal to heat up the reactants. Instead of plug the values of the formula, I get this expression whose graph looks like this. You can see that at room temperature the efficiency is 0 as expected. And at some high temperature here in 2000 Kelvin also the efficiency goes down to 0. This would probably cause a problem related to manufacturing steam as well. But our coal power plants do not work at such high temperatures. We somewhere around here. Okay. Somewhere around 800 Kelvin, that range. And the efficiency, I suppose I've got 1000 into the efficiency over here. That's roughly 450. Okay, which is divided by 0.45. So 45% efficiency we are getting at roughly the 500 degrees Celsius. How does this compare to a real coal plant? So a real coal plant can get a modern coal plant built very efficiently, gets around 23% efficiency and a very similar temperature range. If you want to design a real coal plant, you will have to take into account multiple other things such as, for instance, the various equilibrium that coal exists in, with carbon monoxide, carbon dioxide, spurious side reactions involving sulfur in like in the coal. Like normally we work with something known as bituminous coal. That is not 100% pure, nor is it as poor as peat. So it's all about something. So we have to take all that into account to get a real coal plant.
Where is the mass efficiency?
Where is the
Max efficiency.
that you can see from the graph and 800 Kelvin, approximately that range. Right, so well done.
This is pH versus
That is efficiency versus pH. Okay. So this is going to practice and let's slowly method. So now what is that? What is the fundamental constraint again? The temperature of the reactants. Okay, temperature of the reactants is the main constraint. We need to think of, or at least we think that is the main constraint. We need to think of some way around this, right? Because look, I just tell you the final goal here. Our final goal is to build a extremely efficient engine, the ultimate efficient engine, and see whether there is some fundamental principle that tells us how much that efficiency is. So what I do for now is just try to incrementally improve efficiency. One step we can do is to increase the temperature. The issue here is that okay, we have to give a lot of heat in order to maintain that hot temperature. Rather than doing that, one other alternative idea just stays out. Okay, I'll try something like this. So the first step, I will take my reactant seed at room temperature. So this setup is a little bit different from the reaction chamber before. What I have here is a sort of a chamber with a lid on it, a movable lid. Okay, this is like a piston and a compression chamber. The movable lid is what we call piston. Okay, and I put my reactant inside this chamber and firstly maintaining a constant volume, I combust it. Okay, I combust it. And then I run this through a Stirling engine and I let this cool back down to room temperature again. I let this cool back down to room temperature. And I try to extract as much work as possible out of it. Now, it is still possible that you see that so some many reactants may either increase or decrease the particle number. Right? So after cooling back down to room temperature, it may be so that the pressure inside is different from the atmospheric pressure. This gives us one more opportunity to extract a little bit more work. So what I will do is I will perform an isothermal expansion and try to get that to the work also. Okay, let's see how much this will use. Okay, I can't indicate a diagram also what's happening here. So first there is a constant volume compression. Then slowly at the same volume, heat is extracted out by a Stirling engine. And then it expands isothermally to some final volume, and then you can remove the exhaust gas out. So this final step is the removal of exhaust gases. Okay. So I'll take an example. Suppose I will take a simple example of octane. Octane is so petrol is like majorly octane, that's the octane. Okay. And we'll just go to calculate to see what we can achieve. Many of our car engines now work at 40%, 50%, 100% that is better for a modern car. Here we will see we are actually getting much more efficiency, but there are some little caveats. Okay. At this point, I see the next two calculations we will be messy. The work done I can write as one special heat into this is the how much I will extract, and I can integrate that as I go down to the room temperature from the whatever topmost temperature component is produced. when I calculate everything, right, I am calculating first to reaction. So this is your petrol, okay, CH means petrol. Burning is oxygen to give water and carbon dioxide. 8 plus 9 is 17 mole gas over here, 12.45 mole gas over here. So okay, there is some reason for further expansion. Enthalpy change is 5,470 kilojoule per mole, right? And I get an efficiency of 82.6%. Which now at this point we have to stray a little bit away from what is practical. The issue here is that the final temperature I need is 6,475 Kelvin. Okay. For achieving this, 82.6% efficiency. I know not in practical, but that's okay. This is theoretical, right? This is the efficient that we get.
Everything was going on. Like, okay, so we have one chamber there, and like we are slowly heating. Like there's a reaction that's going on in that chamber.
So I'm keeping at constant volume when I'm doing the reaction. Why am I doing constant volume?
Because you get maximum heat, like maximum temperature change.
Okay. And then now we have got a lot of heat, right? Now we want to extract that heat.
Yeah. So the temperature, the engine will keep on changing depending on the temperature of the container.
Yes.
So that's how you integrate it.
Yes. So the engine will go down. So the previous case you were maintaining the engine at high temperature, but that we have seen caused a lot of waste and heating the thing down. So we are good.
Changing the engine temperature based on that.
Yes. Okay. If you look at the previous cycle, right? Heating the reactor, this is a reversible process. Go ahead. So that was not previous case. Okay. So we try to not waste that much. Okay. So I'm doing integration, and then finally going to calculate the total work. Let's just do the calculation again. Let's just do the calculation again. I'll tell you one of the ways to like. Okay, so the work current expanding is some pressure in some delta volume. Okay, delta volume is at the final the room temperature only. Now you see that delta U, and when you integrate this HCV into change temperature from delta U, so that will get delta U and delta H. Exactly a room temperature, right? Remember the expansion is a room temperature. So this is, I mean, what is delta H? Concentration heat rate. If you remember the calculation of heat concentration delta H. So when I add that work term, I will get the delta H. Then there will be some more terms over there. You do that. And this is the total work that we will get X. And as you can see, we cannot extract delta H. So what is the delta H? We will see that one. And that is efficiency 82.6%. Now, I must ask that, yes, how is this ability to give the elimination the efficiency of the previous case, right? See, the primary reason why this eliminates the efficiency of the previous case is that we are achieving a much higher temperature. Maybe focus on it a bit. We are achieving a higher temperature here. But if you ask me, is this a reversible process? Can combustion be a reversible process? Is combustion reversible? No, right? Can we hope to get a very high efficiency engine through combustion? What are the options? If we can't combust, how are we supposed to get other energy, other efficiency? Combustion is what? Yeah, see, combustion is like, I mean, you can take all any reaction for instance, right? What kind of reaction? So here we are taking, for example, decomposition reaction. We have some TNT decomposed, right? That is like what? All these neatly ordered molecules will come in simply smash them apart. How is this reversible? This is like we are increasing the randomness over here. You know, if you use sort of analogy which we will again come to the line. If you want to fight a war, what is the first step? You have to make your soldiers a little bit, organized, disciplined, directed, right? But here we are basically trying to fight a war and extremely disorganized soldiers. Rather than trying to give some sort of discipline to them, we are doing the exact opposite. We are making our entire system more chaotic. How is it supposed to give us more efficiency? Okay, so we'll come to see whether there is a way to, we have a fuel, can we somehow extract energy without combustion? We'll think about that a while. But before that, let's just look at this, right? We'll know that a while. First, let's look at this a while, right? We have got one temperature here. This whole thing is here, right? That's the thing. Sorry, wait. Okay. Let's start with this. How can we, so we have a temperature booster for this one. Can you think, we want even more temperature? Let's start with that.
What can we?
So we want even more temperature.
Even higher temperature.
We want more temperature. Think what temperature is what we want. Can you think of a way to do that? Decompressing. Okay. Where are you going to get the energy for compressing it from? So, it's closer that way. So, there is a concept in engineering. Whenever something is not working appropriately, then you have to apply feedback to fix it. Very good. Where they get the energy required to compress it from to 25 people? No fuel. What anything. We didn't get regarding flow there. Which where over here we get the energy from? Yeah, someone is taking the imagination state to understand this. So where do we get our extra efficiency from? Our extra energy from? Or compressing it. But clearly if you want to increase temperature, I know through something that is not a chemical reaction, the compressing is the only way to go about it.
You speak with slower.
So clearly, if you want to increase the temperature, and suppose you cannot allow to do a chemical reaction to increase the temperature because the fuel is an interrange, only way to do that is to compress it.
So you try to compress that chamber to the left so that the temperature increases.
Yes. So from where can we get that energy? So the thing is that we have to push it back, right? So when we are intaking air, we put weights, right? When this volume is reaching a zero,
You have to pull the piston back up again.
right?
Because it has to be cyclic.
Yeah. So that is the idea of feedback. We get output and use the output to grow the input. So we take some of the work that we get as an output over here, right? And we put that work back into the engine. Won't that reduce the efficiency? Okay, let's think about that. So when you take some work here, okay, you're putting it back over here and compressing it more. And increase the temperature over here. You combust it, temperature even higher. Now with this high temperature, you are able to extract more work. Right? Once you have more work, you can put more back here. You are again able to extract even higher, because it's better you can extract even more work from that. Of course, there is still exchange, so if we compress it too much, then it may, there is not very linear feedback, it will hurt us. So there is some optimum amount of suppression. Okay.
Wait, so you're saying we do a reaction, we'll combust, and after it has combusted, we'll compress it even more.
Yes, let's see how it happens, right? So what's the first step you were saying?
It won't be a constant volume process anymore. So it'll be like you change the pressure, you change the volume as it. Is that what you're doing?
I mean, anyway, the volume is changing in this step. Okay, yeah, changing the volume. How do you put it? So how do you modify this?
I'm going to modify this. So it's
Right. So we have a work here. First, what will we do? We will take our iron side, right? We'll take our iron side. And then we will take iron at atmospheric pressure, so there's no work running, doing that. Okay, and fuel now we take it at atmospheric pressure. Next, so do we compress it before or after combustion?
After the combustion.
Okay, we will do that.
combustion, the thing is that the pressure becomes very high. Because after compression, the pressure is, is very high over here.
So like we compress it before combustion and then we lock it in place.
Yes.
Okay, but then the temperature increase won't be as much, right?
Because the calculator,
The temperature increase depends on like PdV, right? So then, like if you're compressing it at high pressure, then you get a higher temperature.
again, when we calculate CC as it's not the temperature increase. If you're compressing at high pressure, that will mean a lot of work done. A lot of pressure is putting work done. You don't come to high temperature, not enough. You have to make the work. Okay. So let us finally we have to calculate and see what happens. Okay. Calculation is a little bit messy. We'll come to that. Firstly, let's understand the picture what is happening. Right? The first step is okay, we are taking in at atmospheric pressure, we are compressing it down, and then we are compressing it down. See, then it is combusting at a certain constant volume. Stirring engine is extracting as much of the heat energy as possible, brings back to room temperature, and then from this even more compressed location, it is expanding back up to the final state, at which the exhaust gases are at atmospheric pressure. Right? Whatever tiny volume is over here, they expand hydrothermally because the exhaust gases come by atmospheric pressure, and then after that is over.
So in a way, we just have two engines side by side, right? In a way, they just have like two engines side by
Yes.
side.
Yes, let's see okay. Well, that's good. So, whatever I've been showing my hands, and I hope you've been imagining that.
Conventional machines don't work because of efficiency.
Machine goes out for efficiency.
Isn't this in a way of conventional machine?
We wanted to do to make it work, right?
Brother, we have to when the compression part increases temperature. That is the part itself is sort of a conventional machine.
No, so think about it. You can't keep on compressing forever. If you compress too much, then you are actually losing on work. Okay? So it is not it is an improvement in efficiency. Okay? That's it. It's not as if you are completely there is no complete machine.
It's a output of studying
Yes.
to increase the output of studying.
Yes.
So there will be some losses in using the work to compress it. Won't matter.
See, vertical motion comes from three types. Right? One is when you are disobeying the first law. You are creating heat over nothing or energy over nothing. Right? Machines using do this are known as propulsion motion machines are the first thing. They will create heat energy out of nothing. People in the 16th century were busy trying to create this. They were at some point they became equivalent to alchemists, no use. The second kind of propulsion motion machines are, second kind. Okay, these are machines which can get more than Carnot's level, let's just put it that way. Okay, they can extract all of the, or at least more than Carnot took the heat of some source. Here also that is also not happening. Do you agree?
What I'm trying to ask is that machines which are which show that they are infinite.
Well, not infinite also. Okay, and this taking some of the output work, putting it into the next cycle. That this decreases the total output work. That's right. And our hope is that the increase in temperature that this gives us will compensate for that. Right? There is no confusion about the idea. We are hoping that. Okay. Okay, so this is the implementation of that. Right? We can see that the first step is we are doing intake. All our gases we are taking it. Second step, we are using some verb to compress it. Some verb to compress it. Right? And now the third step, we are combusting it. We are removing the energy from swirling engine, and then we are learning to expand. Okay? And in the final step, what is happening is all the exhaust gases are removed. So this is a simple indicator diagram of it. Right? Starting from zero volume, we take in our gases, we compress it,
then it combusts, then the stirring machine moves for the work, and then it expands, and then the exhaust gases are moved out. Then
Can you explain?
in which part, the cycle or this one? Cycle. So here we are, the green refers to taking in gases. This one refers to compressing the gases. Now we are combusting the gases, that's what I call as power. Now we are using the stirring engine to take out some of that energy. And then it is expanding out. And finally there is again exhaust is not removed. Okay. So this is the final cycle. This particular engine is known as a 4-stroke engine, right? 4 strokes because what is strokes? Okay, 4-stroke engine. Fine. Now the calculation for this engine is a little bit messy. Okay, so I don't want to spend more time on doing it. I'll just show you the final result, which is plotted over here. This is a plot of the efficiency versus the temperature raised to 0.5. I had to do this just because otherwise it's not very easy to see. Okay. So you can see that there is a certain temperature. Right? That temperature corresponds to I think roughly that's 150. So 150 squared. So roughly at this temperature is to 0.5, right? Just for making it easy to see. So roughly at around 150, that one square is also 22,000, 26,000 Kelvin. And roughly that temperature we are going to get our maximum efficiency. Is 23,000 Kelvin feasible? I mean, our engine is going to atomize and perhaps become plasma also at that temperature. But anyway, at 23,000 Kelvin, we get an optimum working engine. The efficiency of this comes out to be 92.6%. This is still less than what can be achieved with petrol. Okay, this is still less than what petrol can achieve. But fine, that is this one engine. Okay, now suppose we want to make a practical engine. There are a few different. I'll just quickly go through practical engine and you get over this. Right? One thing is that we cannot burn petrol with pure oxygen, right? Because we don't have pure oxygen around here. What we have is nitrogen is to oxygen at a 4:1 molar ratio. So what we will have to do is we have to make an engine that works on that. This engine is definitely going to work at a lower temperature. Why? When we have to, when our working fluid is a mixture of oxygen and nitrogen, can someone tell me why this is going to hurt the maximum temperature we can work at? Nitrogen mixture basically we use this over here to absorb all the heat. Okay, so that is one thing we have to look at temperature. Apart from that, there are other factors, chemical factors. So 23,000, well before that, water, carbon dioxide, all would have dissociated to atoms. And when you dissociate, that is another reaction. So it will not never actually reach that temperature. In reality, we managed to achieve around 2,000 Kelvin max inside a real engine. And let's see what real engine is like. So the cycle is somewhat similar, right? We start with what? We start with an intake. So we do that. We start and we take some energy. Then we compress the gases. Right? And maybe we should call them right? First, let us imagine fluid. So first I intake the gases, then I compress it, then I combust it to some maximum pressure, temperature, and so on. Now at this point, so at this point we got to attach a swirling engine to it. But can you think of what the issue is with having 2000 Kelvin gas and trying to pass it through a certain wall in order to power the swirling engine?
There will be losses through the wall.
Yeah?
Losses through the wall.
It will?
There will be losses through the wall.
Yes, there will be huge losses through the wall. There will also be radiation losses, which cannot be pure at that temperature. And finally, the wall will also get destroyed. I mean, if you look at it, here we are having this sort of lid which has to go up and down. Right? Getting a tight seal between the lid and the chamber. This is another practical issue. How will that happen in 2000 Kelvin? So in reality, we are not actually able to go beyond some 400 degrees Celsius at the chamber. If you go beyond 400 degrees Celsius, the pressure will destroy the walls. Unless you are willing to pay millions of dollars, you won't get a useful engine. So what is the solution? Somehow want this, okay, 23 is not possible, at least 2000 Kelvin we want. But our walls are not able to handle more than 400 degrees Celsius. What is the practical solution to this? So for good efficiency, we want very high temperature. 23,000 Kelvin we cannot do. 2,000 Kelvin we want. But our sprinkler cannot handle more than 400 degrees Celsius. So what is the practical way to resolve this problem? Lot of thermal insulation, the issue is that the walls are handle it. Insulation means that process, okay. So it's actually we do need a certain type of insulation when you want it. We are having insulation, but actually not allow us to pass heat energy out to make a stirring engine. So we will definitely have to change the process. So rather than having this stirring in here, because we need insulation, we are kind of forced to use an adiabatic process. So rather than passing heat to the stirring engine, what we have to do is we have to expand the gas adiabatically and hope to get work out of that. This change is inevitable because it's just not possible to pass over heat through this wall. Now, what kind of insulation is another question. One of the good things about so one technique is we can do a thing very fast, right? We can just we do it so fast that the cylinder is contact with the gases for some time that it does not get hot. That's the other option. Again, stirring engine is a very slow thing. You will see how this works and we keep on rotating. So it's not possible to use stirring engine at that speed. So again, we are forced to go with an adiabatic process. But two things we do fast. Many large games we do very fast. Secondly, as for the insulation aspect, when the gases are moving and combusting very fast, one kind of helpful phenomenon which develops is something known as boundary layer. So as the combustion happens, there is the cylinder, near the cylinder walls, there is this layer of cold gas which form, and so the hottest combusting gases don't actually come in contact with the cylinder. So that was the way like us. So, but of course, one change that happens when we do this is that we are no longer relying upon a heat source and trying to extract work out of some temperature gradient. Instead, our work is being extracted in the same place where our combustion is happening. Get the difference? What is the function? So, firstly, we have that we are forced to use an adiabatic process in order to make something practical. This insulation for adiabatic process is created by a certain boundary layer in the gas. Right? To properly understand this, you have to study the dynamics of this. Okay? And the combustion as well as the work production is happening in the same site, not in a different location. Okay? In the steam engine, the combustion was happening all the way over here. There was this intermediate gas for some reason, and here was where the work was coming. And this is attached to your train order. But here we are having what is known as internal combustion. So this kind of engine is called as internal combustion engine, and this is the indicated diagram for the internal combustion engine. Okay. So in order to launch the chamber when the combustion reaction happens, and there is a stirring engine and has high temperature heat from the chamber walls, and adiabatic expansion that happens very fast to minimize transfer of heat is used. The cross section of the internal combustion engine is given here, just as you can see. This is a real life engine. These are the engines present inside a car. The mechanism at the bottom is something known as a crank. A crank is a mechanism which can convert this up and down motion of this cylinder, which is called a piston. Then it converts up and down motion into a rotating motion. Right? Let us not get into details of how that works. But that's how it is. On the top, you can see multiple holes over here, right? This hole is already, I think it's inlet manifold. So all the gas in the atmosphere enters here. Over here, there will be two valves. So those are for maintaining the fuel and everything. And then there's an exhaust valve, an exhaust manifold where the exhaust gas are removed. Okay. Also, by the way, the internal combustion engine is not it's not like this is the only engine. There are multiple different types of internal combustion engine. I'm going to show you one. Okay. There is the Rankine engine, the actuation cycle. Right. So multiple types of engine are there. I'll just quickly go to the most common one so that we can get some idea of Number one, it is not possible for the cylinder to handle 2000 degrees Celsius or Kelvin, sorry. So, if we have a process that is, let's say, non-adiabatic, through which heat has to pass through the cylinder once, that's not possible. Right? Because the cylinder does not have to reach 2000 Kelvin. Right? We can have gas which is at 2000 Kelvin. And so, what temperature can pour efficiency? It is good for us. But the cylinder does not get disturbed because the cylinder itself is much lower temperature. Okay? Yes. What is the point? So we are actually transferring heat, as you will see. The heat is transferred directly to Earth through expansion. We are not going through a Stirling engine that is there. We will again, when also we do the math and see what happens. Yes. So Stirling engine gives us a negative by 3% efficiency, but it's not practical. So we are trying to modify that to be something practical. What is happening here is thermal, right? Whatever heat has been generated in combustion, in the adiabatic process, all of that goes to work. So therefore, heat flow. Okay. So this is a full corollary engine. Look at that. One small practical difficulty there over here. You see that there are these three volumes of interest. Right? So this is the volume in which the combustion happens. There is one volume at which the intake finishes, and then there is a different volume at which the engine ends up after the final power stroke. Why is this? Anyone defines this? Yes. Number of particle changes. That's a good one. So there is going to be a difference in the volumes. This is so we can fit engine which takes into this into account. The activity cycle kind of is a bit. Not just that the particle changes, it's also true that at the final, at the final pressure is the same. Right? But yeah, so if you expand the atmospheric pressure, because the number of particles changes, we will have a different volume. This is great engine which works by based on this. It is a little bit, what we say, it's been found to be a little unreliable. Unreliable as in the mechanism needed to control the piston to move carefully across those three volumes. That mechanism is a little complicated, it will break easily. A lot of repair work, a lot of maintenance cost. So normally we go to the cycle, simple cycle. What we do is the same thing. Right? We take, compress, combust, expand. But here we stop at the same volume as before, rather than allow the expansion complete. And then we just give up our heat or just go back to the exhaust. So we push our exhaust out and the heat is simply wasted off. It loss of efficiency, but then it increases reliability. So that is our real engine. Okay. Are we clear up now? So this is our real engine. We have so let's talk about the basic need. This engine was made in 1976 by Otto something. James Otto. Okay. He was a full name. Very. So this cycle is the engine on the Otto cycle after the inventor. This cycle is more inefficient than the previous cycle as you see. Wastage over here. But of course there are some simplifications. Since there are only two important volumes, that simplifies making the piston. Simpler and more reliable crank mechanics is used, hence is more popular. And at this point, we would continue a little bit more on this. Right? And then we actually just complete some of the basic aspects. What are some of the small issues about the cycle where there is wastage? That's also basic, right? So one fact, okay, there's basic heat at the end of the expansion, yes. There's a heat, then the exhaust gas, you can see, ends up at a higher pressure than the atmosphere. So, okay, then you will have to push this gas out. That will also be a wastage. Then there is what? Now we have one more thing. We are not going all the way down to zero volume. Why is this? It is difficult. Same thing, it's difficult to manufacture something which goes all the way down to zero volume. You know, all the this to the bottom. Not only that, it is again the mechanism. But if you don't go all the way down to zero volume, what does that mean for the exhaust?
There'll be some residual gas remaining in the oil.
There will be residual gas. So this is also one of the problems. Right? The residual gas mixes with the incoming fuel. And finally, we have fundamental limitation, temperature constant 2000 Kelvin. Okay. For better performance, we start to go for better values. But yeah, these are the limitations. Okay, let's just take one example. Let's get some idea of engineering. How do you plan on fixing the residual gas issues? I mean, we can't go down to zero volume, but there will be some that. And there are multiple ways that means also regarding resistance.
We can flush out the gas with some other gas.
With some other gas. Okay, good idea. We can flush out the gas. With what gas do we flush out the residual gas?
Input atmosphere itself. So we have to also definitely we will need a separate input output one. Okay. I mean even if we use the same one, it's just mainly has to keep on switching the plate. So we have to separate one for input and one for output. For the inlet valve and the exhaust valve, both of which are controlled by the camshaft. And yes, that is one good idea. We flush out the exhaust gas using the input gas. This how we can achieve this is our other difficult questions, right? We have to be very careful about how the shape of these the input how the shape of the input valves are, how the air flows when it enters, and the shape of the piston head, all this you have to be very careful about. So there's a lot of engineering there. There are two ways to go about doing engineering. If you were in the 1940s, 1950s, what you would do is you would first make a simple engine with calculations and ignore all these effects. And then one by one you will take this thing and put it on something called as dynamo, and you will measure the output horsepower, and based on that you will see, okay, if I increase the watt diameter this much, horsepower is what effect am I having? And then you keep on tweaking the engine again and again, till it becomes something that is works good on the market, and you are happy with, and then you will sell it. That is how you will run also. After 1975, there were some changes, right? The story goes like this. I'm not too sure about this, but there was this Ford Motor Company, right? Ford Motor Company wanted they were interested in getting into the field of racing, right? Why? Because it's not a national break. Everybody used to have their own good race car. So they thought, okay, I will go and buy one for a race car. That's the easiest way to do it. Yeah? So they went and tried to buy Ferrari. And Enzo Ferrari, the owner, he was a little bit adamant and a little bit rude also, you could say, or at least rude in the race. He wanted full control over the racing aspects of the company, which Ford did not like. And the entire negotiations grew up, and the Ford CEO was like very angry. Right? And so he look, I need you to make the race car for me, and give you billions and billions of dollars. Right? And he was just one guy named Shelby, Robert Shelby. Yes. And then they went on building the car. These billions of dollars were spent on a new technique of developing engines, which is through intensive computer simulations. And they built a car which beat the Ferrari's car in 36 seconds, and then it died off. Okay. So that is the other technique. You use a lot of simulations to model the flow of the gases and build it. Okay. So that is a bit about this cycle. This picture here shows stage of the cycle. Because here is the top. Now it's compressed with the gas. And then expanding. Now it comes back here and compresses the exhaust and throws the exhaust off. So on and so forth. Okay. I will not try to analyze the efficiency of this right now because there's more ahead to it. This efficiency analysis can be done. So this thing is, this one is an adiabatic compression. This is like a constant volume of heat, another adiabatic, another constant volume. We can take few approximations and treat this as a heat engine and try to figure it out. Okay. You will see that the practical limit for most cars is somewhere around 50-55%. The The reason for this is because again, primary temperature and then other factors. Okay. Now let us try and really aim for the maximum amount of efficiency. So in order to get more efficiency, one way is to heat the gases a lot. What is the other way? We can make rather than increase the temperature of the source, we can try and decrease the temperature of the sink. As we have seen, a Stirling engine works both ways, right? You can so if you give in some work, it is possible to reduce the temperature of something, right? And so one alternative technique to try and aim for more efficiency is to do some of this work to decrease the temperature to some very low value, run the reaction with a low temperature, and then heat it up or something. Let's see. Maybe one alternative approach. So rather than going to high temperature, we try for low temperature. Temperature equal to infinity is not very feasible. Temperature equal to 0 looks closer. So let's search that. So this is a preliminary search. Okay, this is to take a sort of preliminary look at it. Right? Not make a full engine, just one small, just to test an idea whether it is reasonable or not. Right? Leave the first seconds. So now let's suppose that I have 0 Kelvin, the source over there, the sink over there. Right? 0 Kelvin sink is there. And what I do is I take my reactants over here and convert it and I run it through the engine. What happens? The efficiency is perfect. That means all the heat energy gets converted to work. Is any energy deposited in the 0 Kelvin sink? Is there any energy deposited in the 0 Kelvin sink? Nothing, right? Nothing is deposited in 0 Kelvin sink. Does this look a little bit suspicious? I mean, because as well not sink is a trade. When sink is not accepting energy, why do we just not have sink at all? And then somehow you work on nothing. So what was going on here? So if we continue this, we will eventually be able to convert all of this to work. This will go down to 0 Kelvin. This will also be 0 Kelvin. Yeah, you know what I created right now? I created a very wrongly. But if I take this 0 Kelvin sink along with the piston and I move all over the world, one by one I can suck up the heat from everywhere and do whatever I want. So what is the issue here? There's some catch here. What is the issue? We do black box. Anyone has the idea? What is the black box here? Yes, what is the difference?
Delta T small.
Huh?
Small delta T.
Small?
Delta T.
Small delta T. I mean, they can take different delta T equals to 0. But okay, that is one possibility. So what you're saying is that the ordinary things which are like restriction and all that are delta T being finite. Some are like that. What is the other possibilities? That's not exactly the reason. I mean, I guess you can take it.
You can't pull the reactants down.
You can't put the reactants at 0. Well, you can't get very close to 0. So, leaving that suppose that I give you a 0 Kelvin sink. I give you a 0 Kelvin sink. No. I mean, we are forbidden from going to actually 0 weight. Wait a second. But 0 Kelvin sink is there first. Somebody do this first. So which law? Normally look at this search of the laws of thermodynamics. Alpha. Third law. Okay, what is the third law saying? Okay, molecular motion sees at 0 Kelvin. We will take that into account, yes. But that is not exactly the statement of third law. What is the statement of third law? This law is not covered in the school, so what is the statement of the law of thermodynamics? So,
See, okay, anyone else want to try? Okay, see, there is various platforms that we try to create orbital motion machines. Orbital motion machines, the first kind are those which break the first law of thermodynamics. No, we are not breaking the first law. Right? The energy is going from E to one side. Orbital motion machines are the second kind, trying to break that law of thermodynamics, which states that it is not possible to create an engine more efficient than a Carnot engine working between two temperatures, TH and TC. That law is also satisfied here. Right? Only T equal to 0 Kelvin. So that was also not broken. So the issue here is that, let's be clear about this, the issue is that we are making a mistake in assuming that at absolute zero, it is possible. I know the mistake is this, that at absolute zero, it is possible to create a finite change in temperature with the infinitesimal or zero input heat. Okay, and let's do this carefully. At absolute zero, by giving zero heat, I am able to change the temperature. What is this thinking carefully?
CPU is 0.
At 0 Kelvin, we can give zero heat and get a finite change in temperature or some change in temperature. Entropy is why is it supposed to be constant? Which is very to observe these situations.
Specific heat is not 0 at 0 Kelvin.
Not zero or zero.
Non-zero.
Zero. For you're getting like some heat, like you're getting no heat.
Yeah. So like in our assumption, we took it as 0, but practically it's not 0.
No, actually it is zero. That's why it is.
Okay, fine.
You're telling the opposite. Right? When I say that with zero heat, I can get finite change. That means what? Delta Q by T is zero. The specific heat at 0 Kelvin is zero. That is what allows us. That is actually the real platform here. And the third law of thermodynamics, there are multiple statements of this. So one statement of the third law of thermodynamics is that at 0 Kelvin, the specific heat is zero. And there are, or you could say that specific heat tends to zero as you go to 0 Kelvin. Okay. So the issue is that in our various steps, right? As I go down to 0 Kelvin, we see that there are steps where we give a small amount of heat energy to the compression step, right? From the things we are giving some heat here, not even taking some heat, right? And as you go down to 0 Kelvin, that heat becomes smaller and smaller, but the ability of that heat to change the temperature also becomes more and more. So you never actually reach the fraction of possible. So this is the catch that we are looking at, right? And I explained the boat company. So consider a falling engine which has 0 Kelvin reservoir and some body of temperature T. As well as heat has to enter the reservoir. This setup here is acting like a zombie, sucking up all the heat from objects around it. Right? This is what you call as a complete entropy sink. If the specific heat was not zero, right, and you're not taking the concept of entropy yet, but if you take integral of del Q by T, and if del Q is finite, even if you keep on going up to zero, del Q by T goes all the way up to minus infinity. And you get extraordinarily low entropy here. And because this entropy sink, really everything is possible. Right, so third law basically says that look, these kind of entropy sinks are outlaw. You must have a constant minimum entropy. You can't keep on having this kind of black hole entropy. Because singularity entropy is negative infinity. Entropy must approach some value. Right? Otherwise you will have these kind of zombies. Okay, this third law of thermodynamics of rockets, I want to improve it now. Okay, so the catch is that the law of the third law of thermodynamics states that at 0 Kelvin, the temperature of body and there is no heat input. Okay, there is one more catch which we will come to in a while, which is that the act of combustion is inherently irreversible. Right? So, like the irreversible constant volume step of the Otto cycle, combustion is also an inherently irreversible process. So, let's see, we will try to find a way around that. Before that, this is a very explanation of the third law of thermodynamics. When you have 2 points of T1 and T2, and this body gives out a heat of C C1 dt1. C1 is a specific field of the first body. Second body will receive qt2 by t1, right? Because of the car on time engine. Yes, sorry. So this one here will be C1 t2 by t1 dt1. Right? So I substitute the value of q, which is equal to C2 dt2. We put them together, we will get this integral over here. So we integrate from the initial temperature of this to its final temperature Tf, and we integrate the initial temperature of this to its final temperature Tf of this specific heat dt by t. Right? This again, what is this? You realize this? Entropy. You can do this. You can understand that. Entropy. So entropy. Okay. So and you see that if this integral, if you take this integral, let's say this is the whole body. This is the whole body. If this particular integral, I want it to be equal to this one, and I want the two bodies to equilibrate at a non-zero value. If these two bodies will equilibrate at 0 Kelvin, that is the obvious situation, right? What we want is these two bodies to equilibrate at non-zero situation. For that, this integral here will be finite, and for this integral will be finite as T10 approaches 0 Kelvin, right? As the temperature of this approaches 0 Kelvin. For this to be finite, clearly C1 by T1 must also be finite, so C1 is equal to 0. That's the law of thermodynamics. Okay. Any questions? Solution to that? Where are we getting? So the thing is that eta is very much equal to 1. That is, there's no second law is perfectly valid. The issue is that there exists no heat sink which can maintain a temperature of 0 Kelvin. Even if it receives a little bit heat, it is immediately gone over 0 Kelvin. So second law is very much valid. Eta is 1, but so momentarily, even a little bit heat enters, no matter how fast the heat sink is, it immediately goes over absolutely zero. This is a difference between 0 Kelvin and temperature. So and this particular zombie is the propulsion motion machine of third line, also disallowed. So any more questions? Okay. So our main goal was to try and conduct a reaction at 0 Kelvin, hoping to get energy from that. We see that doing it by a reaction is not really possible. The specific heat is the issue there. So we want to do reaction at 0 Kelvin. So instead what we do is, to begin with, we do reaction and hope to get much efficiency, right? So is there a way by which I can do this reaction without having to, let's say, go through this constant volume process and so on? I mean, from this point we have to do beyond thermodynamics, and I think what happens at 0 Kelvin. Is it possible to run a reaction at 0 Kelvin? Right? I mean, the reaction we're doing here is working. So this reaction is equivalent to like on a desk you place all these very fine clay figurines, so many clay figurines, and you take a big hammer and smash them off. Why you go to all the effort of putting it such a fine nice arrangement and then smash it all up? So the thing will be what happens at 0 Kelvin. It's possible for us to extract energy from it without having to go through the entire process of reacting it and creating a high temperature and so on. I mean, this is actually what happens in reality. You see how this can be done in reality. So, the thing is, the entire purpose of I'm not going to talk about natural steam. They were not natural steam. What is natural steam?
Two systems separated by partition. One is colder, one is hotter, let's say. So, from the colder system, when a particle comes here, you integrate and goes to hot system. From the hot system, when the hot particle comes in, you integrate the cold system, basically like reverse entropy.
some tiny object, right? Who is going to do exactly the opposite of what thermodynamics tends it to do.
Exactly.
So, what is the reason why this is not possible? I mean, we have actually achieved very cold particles and so on. But what is it that prevents this beautiful history?
I believe it has something to do with like information of the even being finite. So after some changes in this state, it must lose the information in order to store more information inside, and entropy is increased there. And this increase in entropy is more than the increase in entropy of the system.
Right, so
Yeah, is that right? Generally, hot systems become cold systems become hotter, but in theory you can reverse that by allowing particles from the hot particles, the fast moving particles from the cold system, when they approach the hot system, you open the gate. So the cold system becomes colder, the hot system becomes hotter. But this theoretically reverses entropy because you are moving against the natural flow. But since the memory of the demon is finite, there must be a step where the information stored in the demon is clear. And when you clear that information, you have taken an ordered system which is disordered, entropy increases.
So you know, like theory, if you want to flip a bit somewhere, that takes up some energy. Some capacitance will restart. Electrical engineering is another example. Biology is a better example. Right? DNA is actually very close to this ideal storage mechanism. Not so ideal, but it takes some energy to store and retrieve information. It has to do with something that is not so clearly thermodynamic yet. Something is not come to get information. So what about zero Kelvin? There's a zero Kelvin, there's a specialty, which is that only 1 meter of information is necessary to zero Kelvin, you basically know everything about the system. That is the specialty zero Kelvin. At least, I mean, everything classically, that's what we do. Classically, we see that at zero Kelvin, all the molecules are at rest. And so we can know exactly where our molecules are. Not only that, they get to actually align in some crystal structure. Right? So that gives us even more understanding of where they are. We know the center mass, we know everything. What is that whole system? At zero Kelvin, we know everything about the system. When we know everything about the system, there is no need for us to retrieve information or process information like the demon has to. We are just simply a demon and we don't do anything we want with those particles. So this allows us at zero Kelvin to take these particles individually, collide them or whatever else, do a reaction, right? And take the kinetic energy of these individual particles one by one and extract that out. Extract as in maybe, okay, we do a reaction, the particles are moving at high velocity, they collide with something, right? And they transfer the kinetic energy to that. And then we do a few collisions till all the energy is given off, and the particles come to rest. In other words, we are like a demon. We can do anything we want with these particles at zero Kelvin. Right? Because there is no need for us to waste our energy in retrieving and storing information. So, and this is not a mechanical contraction. It's not like a Stirling engine and so on. There is no mechanical contraction which can do this. Ultimate efficiency cannot be achieved through the mechanical device. But through all these devices, it is actually possible at zero Kelvin for us to extract the entire energy of the system. And this is something that we will try to exploit in the next step. Create an ultimate engine. What we want to do is to somehow, right, and notice the key point here. At zero Kelvin, the reaction is reversible. If we take two individual particles and collide them, we know exactly what they're doing. We can just put two mirrors here and make them different and go back in the opposite direction, and they will come back to the original place. Our reactions are exactly reversible at zero Kelvin. And this is the only variable efficiency. Perfectly reversible reaction. So I will propose the following machine. Right? This is the sort of machine that we will create. So what I am going to do is I am going to cool my reactants down to zero Kelvin. I will very carefully conduct the reaction and extract all the work that I can. I will be left with products which are also at zero Kelvin. And then I will heat these products back to room temperature because I am very interested in getting our products. By heat, I mean, I will absorb energy and come back up. Okay, so that's what I'm doing here. Of course, we need, remember, each step has to be reversible. So what I will do is similar to how in the Stirling engine has that regenerator with so many different reservoirs, and one step by step we give energy and slowly climb down the ladder effectively. Here also we will climb down the ladder of multiple reservoirs. Right? So here at room temperature minus delta T, room temperature minus 2 delta T, all the way here to 3, 2 delta T, 1 delta T, and then we will climb down this ladder and give up the heat. Okay, so so the blue thing here represents how much heat has given up. All the blue there, that's all the heat has given up. Then we do a reaction and extract certain broken product here. How do we store work? How do we store work again? This is anything of practical mechanism store work. How do we store work? When we extract energy and we store the work there. How do we store work? Okay, spring time. Okay, compressed spring. Or that's okay. So potential energy, right? Also other potential energy. So charge and capacity, that's not it. You can see that here we will take water from tank, that is not the way. And very good common technique in mechanical engineering is to make a flywheel. So this is one very heavy wheel which you are rotating around and around. Right? You store work as the kinetic energy of the wheel. And you will attach to this wheel and slow it down to extract, use it whenever you want to use it. Okay, so we store work over there, right? And now, here's the next step. Okay, so we store work there. Now there is one small issue here. The issue is that we want our machine to be reversible. But we are polluting our reservoirs. Our reservoirs are being polluted. So in order to make the engine reversible, I have understood the concept of the previous steps. Any doubts? This is the most important concept. So, you guys have doubts about the previous step, how we went about this machine. Okay, so now the issue is that with this machine, because of the process of cooling, right? After cooling, we take the work and then we are heating this up. In the process of heating it up, we can take energy straight from the surroundings, but again, we want to do this reversibly. And we already have energy over here, right? So that is taking the surroundings, we try to clean up this reservoir, right? The heating is up by taking energy from here. So all this dark blue that you see refers to energy that is taken back by this particular exhaust gases. Okay, so out of this, on the heat stored here, some part we take it back here. Two purposes, one is we reversibly heat it, second we clean up the reservoir. But nevertheless, our reservoirs still have some energy at each temperature. There is still some leftover energy at each and every temperature. So, to make the engine reversible, you will have to clean up all this energy, right? How do we propose cleaning up these reservoirs? The reversible engine, we need to bring the engine back to its original state. How can we clean up these reservoirs to restore the engine to its original state? I won't give you an answer to this because it's like a good moment to listen to that.
Can you just allow it to heat back up to the surrounding temperature?
These reservoirs are at different temperatures. This is at maybe 1 millikelvin, 2 millikelvin, 3 millikelvin. There is heat stored at 3 millikelvin. You don't want to heat it back up. The reservoir is at 3 millikelvin. You want to maintain it at 3 millikelvin. If the gas is heating back up, okay. But after that, there is still leftover heat. How to do that? Huh? Yeah. How
heat the reservoir back up. And remember, all the way by overthinking here, we want the reversible engine. So how do we reversibly get the reservoir back up to condition? Slowly heat. Reservoirs, we don't want to heat the reservoir. Heat. The reactors have deposited this much of heat. This much of heat. Products have taken back this much of heat. We have this much heat left in the reservoir. What? Okay. Anyways, the idea was happening here. See, our goals have a reaction at 0 Kelvin because that is very efficient. So what we do is we cool our mixture, our reactants down to 0 Kelvin, and I do that reversibly. Reversibly means I take many reservoirs of multiple intermediate temperatures, right? And then I give heat one by one to each of those and slowly come back down to 0 Kelvin. After the reaction, I have some exhaust. I want to, again, everything has to be reversible. So I want to reversibly heat this back up to room temperature. For that, I take heat back from this reservoir and not level go to the top. Now, what are we left with the reservoir? Extra heat. You all agree with that? Okay, so that is very the same definition only. The reservoir is a gigantic object of a certain temperature. That's it. Yes. Cool it down first. No, reactors are cool down, not cool down. Very good. See, I want to cool the reactor down to 0 Kelvin, and I want to do this reversibly. Right? Reversibly means what? I had a big reservoir of 1 Kelvin or 1 millikelvin. The meaning that you understand? Imagine filling this room with the iron which is at 1 Kelvin. That is a big reservoir of 1 Kelvin. With iron at 1 millikelvin. That is a 1 millikelvin reservoir. Right? Use about 1 millikelvin substances. If I want to cool my mixture down to 1 millikelvin, one way is to take this big 1 millikelvin reservoir and put the reactants in contact with it. Right? But what is the problem with doing that? For efficiency.
Not reversible.
Not reversible, right? I will refer that again. You understand why we are cooling these reservoirs? Idea of the reservoir is that we don't want the reservoir temperature to change, so we make it very hard. That's all. We could use ice cube to cool it, but ice cube temperature will change a lot. So it's like going from polarizing contact and vertical. You know that. Right. Reversible is not like a favor. See, the idea is that firstly, reservoir we are taking because we want the cooling to, we don't want the reservoir, we don't want like in the process of cooling the reservoir changes temperature. For a stable cooling, it has to be cooled. The underlying is the reservoir. You know? It's not stirring, it is simple cooling. You could place in contact multiple pads and they cool it. That's all. So it's like these are given first. So we are given a big block of something at 300 Kelvin. A big block of something at 299 Kelvin. A big block of something at 2 Kelvin. We keep in contact with each of these and slowly let it cool down. Got it? So there is no engine problem. Just keep in contact with these big blocks and let it cool down that way. Okay, so like that I have reached 0 Kelvin and start heating up. Now there is this leftover heat in the reservoirs. What do we do with that? Because we want the thing to be reversible. We want the final engine to be back to its initial state so that it can be used again. In other words, this is what we do about the leftover heat. Because no, that's the goal. We want to release heat in the surroundings. But the surroundings are at higher temperature than the reservoirs. We want to release the heat to the surrounding, but the surroundings are at higher temperature. So how do we release the heat to the surroundings?
We need a pump to pump out the heat.
We need a pump. Is everyone understand this? I mean, I think you are getting the idea. He gave it to last and reservoir started. At the receive on the picture, a pump, right? To restore the reservoir state, we use a pump. Where does the pump requires work? Where do we take the work from? From here. Okay, so from here we will take the work and pump all that back to make the engine reversible. So that is what is being seen here. The work is being put into a heat pump. This is nothing but a Stirling engine in reverse, and one by one it takes heat to the wire and puts it back to the surroundings. Okay, can you quickly calculate how much work have we done over here? Delta H, anyone let's do the mind before we see the full calculation. That's calculation. Right? There is some delta H over here at 0 Kelvin. We are obtaining that much work. And the amount of heat that we are sending back up can be what we are taking result of these two. Right? This is how much heat was deposited. This is how much heat was taken out. Difference between these two, you have to restore to the surroundings. Right? And you sum that up over all the reservoirs to find the total heat that has to be restored. That is the heat that has to be restored, but the work that has to be done is what, well, for each liter reservoir you have to do a different amount of work because the engine operates at different efficiency for each reservoir. Each reservoir the engine operates at different efficiency. So let's just do the full calculation. The work done to restore the reservoir is equal to the sum over all the reservoirs of delta NCP. You understand delta NCP? Okay, into J delta T. This is the temperature of the reservoir into PR by J delta T minus 1. This is because it is the Stirling engine is there is some efficiency loss taken off, right?
TR is the room temperature.
Yeah, surrounding temperature. Okay, delta NCP because NCP the difference into this temperature into delta T. Right? That is J delta T into now this is what? That is the efficiency factor. Because the Stirling engine second law applies, you will have to put more work than there is heat that has to be returned. That's the breakup. And heat from the cycle now we can so what is the work that is left over? We have delta H naught work. Out of that, this much work we are using. Right? So this work is being stored in a capacitor and using that charge stored in the capacitor to run a motor. Right? So after 100 delta H naught, this is being used up. And I write this in a very different manner. This minus 1 and club to that. So delta H naught plus summation of delta NCP into J delta T delta T. Right? You want to recognize what this one here is? What is this? Gibbs of law. And then this particular thing here. Okay, anyway, not to the Indian also. For ideal result material. What is the first term represent? So delta H naught plus now there is some this one here, this may be usually confused here. This delta NCP evaluated at J delta T. It's a function. I know. Okay, but remember, this is delta NCP evaluated at that temperature. So CP is temperature dependent, so that's right. Okay. So that will be multiplied by delta T and the adding it up over all the reservoirs. So this is getting Gibbs law. And this is what delta H at the room temperature. And then here we have minus T room into summation over Q by J delta T. That converts into equal over Q by T. And what is that quantity? Entropy. Yes, that is only divided entropy. So this is delta H reaction minus the temperature in the reaction is happening into the entropy selection. And that is the amount of work that we are obtaining. called as the Gibbs free energy. It was invented by Joseph Gibbs, and it is called free energy because it's free. What is free to work? The rest of it is has to go waste. So much we are free to use. Gibbs free energy. There is a video I issued saying, okay, let us think about that. Okay, this is different things in there. There is the formula. So, okay, this is the main result. Let's just look at a few cases. It is just relevant. Supposing that this is okay, understand this one will work. Supposing that the products absorb more heat than the reactants, what do you think happens then?
We can just not use the heat pump and then just pump in heat from high temperature to low.
Okay, look at this way. So here the products are absorbing less. The products are like dark blue. They are absorbing less heat, right? If the products were absorbing more heat, this dark blue will be greater than this. So what you left is you would have in the process of heating it up, you would have taken more heat out of the reservoir than you put into it. So what do you do mainly? Again, that will be
We take some heat from the surroundings and put back in.
and in the process you take the work of the thread. Okay. Oh, that is one option. That is actually the case. So if in such a situation, I mean, so it told us like correct, but that is actually the case when you have, I mean, again, taking certain chemicals which are not ordinary and getting heat here, and T delta is also giving me heat. Are you getting? So the work and is equal to delta H, but plus this T delta S, or what are the same things here? Then what does that mean? Delta is greater than delta H. Is it possible for me to do more work than there is enthalpy? I mean, HT is just defined in terms of stage QT. There is no confusion. It is actually possible to obtain more work than delta H. Okay, so methane, I think there's some methane oxygen engine is one example. You can work in 106%. No confusion is possible. Right? Work you can get more than delta H of work. What about the other case? Supposing that, supposing one more situation let us have. Supposing that at the end of all this, I find that the work is negative. What does that mean? There's not so much heat absorbed, the work is negative. Then that means saying opposite, what happens? Or you can put work in force relation happens. Right? That is what happens in an electron one. So delta T is not the correct sign, you have to force the reaction happen. So that is the other option. Okay. Instead of getting work, you are having to put in work to make the reaction happen. Right. So that is for delta T. This is of course more fundamental than this one. At this point I will leave it. This is the explanation of J knowledge. The more fundamental idea of delta T is that whenever you have some kind of energy which is distributed randomly, some potential energy that is randomly distributed. So this could be, for instance, potential energy in the form of some ion solvent in some liquid, or the potential energy of electrons and anything like that. Whenever you have some potential energy which is randomly distributed, if you want to extract some work out of this randomly distributed potential energy, Gibbs free energy is something which puts a limitation to how much you can do. So that is what Gibbs energy is, and of course fundamental elements. Okay, so I guess conclusion, basic how this engine works, how internal component engine works, once the result of thermodynamics, as well as the free energy of reaction. And thermodynamics, leave this code by Albert Einstein. Thermodynamics is the only physical theory of universal content concerning which I am convinced, Albert Einstein is convinced, and I also actually convinced, that within the framework of the applicability of this basic concept, it will never be overthrown.